you how to model a thermal problem, a heat conductivity convection problem, a simple one. So we're going to model this. We have a composite wall made of cement asbestos brick, and the starting temperature on the cement side is 200 centigrade, and then the brick wall, the outside atmospheric temperature is 30 centigrade, and we have the thickness of the cement wall is 5 centimeter with thermal conductivity coefficient of K equal to 0.08 in SI unit. Asbestos has the K 0.074 with thickness of 15 centimeter, and the brick wall is 10 centimeter. So we're going to do a steady state solution and find the temperature distribution along this wall. We have done this using FEA by hand calculation, and we have the temperature distribution. We're going to use this to verify the results. To model this, we can model this using 4 elements. One element representing the cement, one element representing asbestos, one brick wall, and then one the air, the atmospheric, the environment. So let's start it. This is going to be a thermal analysis. So the element types that we're going to use, we're going to need 2 element types. One is link 33, which is for conduction, and then link 34, which is to model convection. Alright, so we close this. We're going to need real constants for these guys, for these 2 elements, which is going to be the area, cross-section area. We're going to assume that the area is 1 meter squared, the area of the wall we are considering. And then, so for the air, the convection part also, I'm going to consider 1. So we close this. Then next we're going to need to define material properties. So we go here, thermal conductivity. Material 1 was cement with 0.08. 0.08 is thermal conductivity coefficient. So let me type it right. 0.08. Alright, so this is material 1. Material 2 was the asbestos, 0.074. Which is like an insulator. And then the next one is the brick wall itself, which is 0.72 thermal conductivity. Alright, and then for the wall, for the air, the material 4, I'm going to need to define H, which is convection coefficient. That one for the air is 40 in SI unit. So 40. Okay, material defined, I closed it. Now I'm going to go to modeling, create, key points. Okay, point 1, I'm going to start it from the origin. Right, point 2 is going to be where the cement ends, which is 5 centimeters. So the SI unit is going to be this. Then I'm going to go point 3. Point 3 is going to be at 20 centimeters. Right, point 4. This is where brick wall ends, which is going to be at 30 centimeters, and then 0.5 for the air. I'm going to assume that it continues 10 more centimeters for the air. Alright, so I'm going to now connect these points and form lines. Alright, so we have 4 lines. Next, we need to mesh. So to mesh, first I need to assign attributes, different attributes to them. So go here and say this one, line 1, material number 1, real constant. We had 2, but both were the same. So, but we have to make sure that we use link 33 for that, the cement. So I'll do that, and then number 2, I'm gonna do that. The real constant again is this, and then number 3, we're gonna do this, and then for number 4, you gotta make sure that is number 4, and also we have to change the type of element to link 34. Alright, so then sizing, I'm gonna make all lines just one element for each line is gonna be sufficient. Then we have to mesh it. So mesh all the lines, pick all the lines, so we can then come here and see the list of our elements. We have 4 elements with their material properties, the real constants, and sections, nodes. Alright, so we're gonna go apply load. Load is gonna be in the form of temperature. So the cement wall here. I'm sorry, let me show you the statement. We start with 200 centigrade. I'm gonna do it here. 200. That wall is 200. And then on the right side, which is the air, that's gonna be 30. Okay, so we should be good to go to run. Let's go solving. There's the warning. Okay, but so solution is done. Let's look at the results. So nodal solution and nodal temperature. Okay, so here's the temperature distribution, guys. Node 1, 200, which is the cement wall, where we started, and then where the end of this. Let me bring this here. Okay, so node 1 was 200 centigrade. Node 1, where was the interior, temperature. At the end of it, I have 162. Where the asbestos starts, after that, where the asbestos ends, it's going to be 39. So you see asbestos drops the temperature significantly because it's a good, insulator. Then we have the brick wall. From 39 drops to 31, and then air is 30 degrees. So this is matching what I had from hand calculation using FEA theory. So as you see here, the numbers match perfectly, 200, 162, 39.9, and everything matching. Alright, I hope you find this short video useful.